All right, so let's go ahead and continue on with 1.3 here. Let's do an example problem here to show you a good use of the basically knowing the unit circle and using it to figure out other unknown quantities. So here they're telling us basically that we have to find the cosine and tangent. You could also then go from there to find secant, cosecant, and cotangent just by taking reciprocals of these values. But so we're going to just find the three main ones if you want. Take reciprocals of the results and you'll get the other ones. So here we are given that sine of x equals 3/5 and that x is between pi over 2 and pi. So if we look at our unit circle, the first thing we want to think about here is here's our unit circle, let's say, and we're looking from pi over 2 to pi. Well, pi over 2 is right here, and pi is over here. So that means we need to have something in this interval right there. And so what I'm going to do is draw in a triangle at about somewhere over here, just so I have a general idea. And, excuse me, it's going to look, what is this? So maybe, I don't know, just really anywhere over here. Okay, let's say it's something like this here. Actually, I'm not going to do it right like that. I want to do it like this, I think, just a little bit. I know I'm being nitpicky, but anyway, we're going to do something like that. This will be our angle x, and we're going to try and find it then using this idea. So they tell us that the sine is 3/5, and basically we know that sine of something is the opposite side over the hypotenuse. So what we're going to do is treat the 3 as the opposite side, right there, and we're going to treat the 5 as the hypotenuse, and then we're going to, I can't use x here because they told us the angle was x, so I'm just going to put like an a or something. So, and that's our right angle right there. So we'll put an a. That's our unknown side then. Well, first off, we can do this pretty easy. We have 2 of the 3 sides of a right triangle, so I'm immediately going to go Pythagorean theorem. A squared plus 3 squared has to equal 5 squared. And so you square these out. A squared plus 9 equals 25. Subtract 9 from both sides. That's a plus sign. You get a squared equals 25 minus 9. That's a squared equals 16. And then we need to take the square root of it. And so when you take the square root, you get a is plus or minus the square root of 16, which is 4. Which is 4. We're not really interested in the positive version here, because you can see right here, right? We're over here in this quadrant, and we know that when we're in this quadrant, remember, x values are negative and y values are positive. So between these two values, we really only want the negative one, okay? Oops, that was a bad circle. We really only want that negative one. So make sure that's the one you're picking. That's why we drew this picture here. That's why I put the triangle there inside the interval where they told me that x was, inside this pi over 2 to pi, okay? And that's why I did that, because I can see immediately that I want the negative version of that answer. So let's write these out now. They told us that sine of x was 3/5. We know that cosine is going to be adjacent over hypotenuse, and our adjacent side is that a, so it's a negative 4 over the hypotenuse of 5. And then tangent is just sine over cosine, so it's 3/5 over negative 4/5. And we end up with 3/5 times negative 5/4, because dividing by 4/5 is the same thing as multiplying by 5/4. And so the 5s will cancel, and we'll be left with a negative 3/4. And there you go. There are our 3 answers. Real quick, if you did want them, cosecant of x would be 1 over sine of x, which would just be 5/3. Secant of x would be 1 over cosine of x, which is going to be negative 5/4, and cotangent of x is 1 over tangent of x, which is just negative 4/3. So if it asked you to do all of them, that's what the other ones would be. But it only asked us to do the other two, so these are the other two that we have there. Okay, so the next one you can see here is right here. It's asking a similar thing. What I'm going to do is leave that one for you to try, but go take a look at the notes and you'll see the answer. The only thing I'm going to put here for you real quick is unit circle, right? Unit circle. And we're going from negative pi over 2, so that rotates down here. This is negative pi over 2 all the way to 0. All right? And so we have to be between there and there. That puts us down there in that this little area right here. And so use that to figure out what your answers are going to be for that one. Okay? And then take a look back at the notes and check, because I'll put the final, I'll put my workout of it there for you to look at. So next, we're going to talk about periodicity and graphs of the trigonometric function. A function f of x is periodic if there is a positive number p such that f of x plus p equals f of x for every value of x. Essentially what this is saying in a nice complicated math way is that it repeats itself. That you do one thing and it repeats, and then it just keeps doing that same thing over and over as you go to the left or right in x. Okay? And so you pick any point on there, and you can always move the same distance p to the right, and you'll end up back on the graph at the same location. And then that smallest such value that does that is called the period. All right? Think about period. It's the typically referred to, at least physically speaking, it's the amount of time that it takes for something to repeat. So if you're taking your physics class or something like that, it's going to be an amount of time. Like the period of Earth's orbit is 365 days or 1 year. The period of Earth's rotation is 24 hours or 1 day. If you have a tire that is spinning, then the period would be the amount of time it would take for it to make one complete revolution. Okay, and so those are, that's basically what your period is. Amount of time it takes for something to repeat. Here, we're not really talking about time, we're just talking about x. So really, it's just the smallest amount of x that it takes for something to repeat. Also, before we really get too much into this, I want to remind you that the difference between even and odd functions, that f of x equals f of negative x, means it's an even function, and if f or negative f of x equals f of negative x, then it's odd. Okay, so remember that for what we're about to talk about, because I'm going to talk about even and odd a little bit here. So let's take a look at this first graph. This first graph is cosine of x, and if you notice, if we look right along this y-axis, it's mirror imaged on both sides. They're the same, you know what I mean? It repeats. We can go just like this or just like this on the sides, and they're mirror images of each other. That implies that this is an even function, which it is. So this is even. And we can even note the period on it. You can see here, if we pick any point, for example, if I pick this point right here, I can go a distance p over and be right to the same exact point. That distance p would be the period. And I can do the same exact distance for any other point I want. I can take that, go the same exact distance. That is also p over, and again, I'm right back on the graph repeating the same thing, and it works anywhere. So I go this same distance p on any of those points, and I'm always right back on the graph, and the graph is repeating what it was doing. So those are all just versions of the period right there. And you'll notice that it has a length of 2 pi. We started here at 0, and we went all the way to 2 pi for it to repeat. And that would be true everywhere. So we could even start here back at negative pi and go over to positive pi. And that, again, would be a 2 pi distance that we would have to go. And you can see that right here. We wrote period is 2 pi. Okay? So the domain of this function, negative infinity, positive infinity. We can plug anything we want into it. But the range, you notice it never gets below -1. It gets down to -1, but never gets below it. And it goes up to +1, but never gets above it. So our range is between -1 and +1. Okay, looking at the next one, this is sine. Notice that we are not mirror imaging across this, right? This is not, it's not mirror imaging like this. That's not happening. So we do not have an even function here. But if we take this and rotate it around this way, this hump right here will match up with this hump. So we have symmetry about the origin. We can rotate it around the origin and get it to line up with itself. That means what we have here is an odd function, okay? And so that is true. So, you know, if we plug in pi/2, we get 1. If we plug in -pi/2, we get -1. That's this idea right there. Okay, plug in a negative and get the negative of what you would have gotten for the positive value. Okay, notice this also is periodic. It has, again, the same periodicity. It has the same period. P, it's again 2 pi, from -pi/2 to positive 3 pi/2. That's a 2 pi difference. And anywhere else, we can start here and go to there. That's there. You can see it's 0 to 2 pi, very easy, period. We have the same kind of range, not below -1, not above 1, and the same domain. This next one here is tangent of x. And remember, tangent is equal to sine of x over cosine x. So if you divide those two together, this is the graph you will get. Here you have to be careful, because if you notice, the period here, look at how long it takes for it to repeat. If we start here at 0, we're only going a pi amount before it repeats. So for tangent, our period is pi. Our range is -infinity to positive. These go on down. They asymptote to those vertical red lines, and it asymptotes there and goes all the way up or down to -infinity and positive infinity. We can get any result we want for this, but look at the domain. The domain is not everything, because these red lines here, these red lines here, these vertical red lines, they are asymptotes, which means it never actually obtains those values. It approaches them but never gets to them, and then has to skip over them. So we basically have x except for all these half pi values, pi/2, 3 pi/2, 5 pi/2, so on and so forth, and in the negative direction as well. So you have to be careful with that, the domain is not all real numbers. The next ones are the reciprocal functions, and again, if you're doing reciprocals, what you want to do is keep all ones the same. You want to keep everything that's a 1, you keep it a 1. Everything that's a 0 becomes a vertical asymptote, and everything that is going off to infinity becomes a 0. So if we look here, I'm going to start by making a little color here. Look at that spot right there. That's a 1. And if we look on this graph, we have a 1 right there. Here we have a -1. 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 So all of those stay exactly the same. Then everywhere that we have a 0, here is a 0, at -pi/2, here is a vertical asymptote. Here's a 0 at pi/2, here is a vertical asymptote. Here's a 0 at 3 pi/2, here's a vertical asymptote at 3 pi/2. So these all correspond. Big numbers become small numbers, ones stay the same, small numbers become big numbers, and if you look even so far as to look in here, where our number starts at 1 and goes smaller towards 0. In this area, it starts at 1, and instead of going smaller towards 0, it goes bigger out to infinity, because the reciprocal of a number less than 1 is a big number. And so if you take the reciprocals of big numbers, you get small numbers, and the reciprocals of small numbers, you get big numbers. So they flip-flop like that. So if you already know the graph of cosine, you should be able to come up with the graph of secant by following those basic kind of rules. You can do the exact same thing here. Oh, notice the period's the same and everything like that, but we're missing values in the domain, just like in tangent, where we have the vertical asymptotes. You can do that similar sort of thing here with sine x. I want you to try noticing where the ones stay the same, the ones and -1s stay the same, positive values stay positive, negative values stay negatives. Zeros become asymptotes, and small numbers become big numbers, and big numbers become small numbers. So try and go through and see if you can get from that graph down to that one. And then the same thing here for tangent. You can do the same thing to get the cotangent. All right? So your choice is either to know how to do that, how to take the reciprocal of a graph, or memorize all 6 of them. I like to know the top 3 and then just reciprocal them to get the bottom 3. But it's up to you. I think it's a good skill to have. I would highly recommend it. Next is general sine graph. So here we have some sine graph properties. First, out in front, this is A. Remember the range of sine was -1 to +1. So we always get values between -1 and +1. And the same thing for cosine. And a lot of the stuff here is going to work for cosines as well as just sines because they are very closely related, and I'll show you in a minute. But this value A out in front, this is what is called the amplitude. It is, as you can see in this picture, it is how high above this dotted line. This dotted line is typically called equilibrium here. This line right there that I just made not dotted by drawing over it. But here, let me highlight it. This dotted line right here is typically the equilibrium. That's like the center of the wave where it goes just as far above it as below it. And the amplitude is how far above or how far below it gets from that line. And that's this amount right here. Because remember, the range for this was -1 to +1. So whatever number we multiply out in front of the whole thing is just simply going to vertically stretch it. And if you vertically stretch a 1 by 3, it's going to stretch it up to a 3. And so the amplitude will become a 3. Or if you vertically stretch a -1 by 3, it becomes a -3, and the amplitude becomes, again, 3. It's the absolute value of that. All right, that's your amplitude. It's like how tall the wave is. B is called the period. That's this number right in here. And we were just talking about it, and it's this distance right here. This is the period right there. Okay, and you get it by taking whatever is out in front there and it's setting it equal to 2 pi over b, and b is that period in the bottom. This comes from the idea of something that's called angular frequency or angular velocity. Typically it's the number of radians per unit time or per unit distance that the graph is happening over. And this actually then, by doing because this is radians per second, to actually convert this into number of cycles per time or per distance, we actually have to multiply it by 2 pi, and then what we end up getting with is omega equals 2 pi f. This f is not the same f as a function, but it's actually something called the frequency. All right, frequency is the reciprocal of period. All right, which means we can immediately write this as 2 pi over b. So if you see a number right here, this 2 pi over b number, that is just actually typically called the angular velocity or angular frequency, depending on what this axis is right here, as to whether or not it's well, not that axis, sorry, what this axis is down here, whether or not it's a time or a distance. But basically that's what that is right there. You don't need to know this. You don't need to memorize this at this moment. If you're ever going to take physics or something, then you're going to want to know that. But for this class, you don't need to know that. I'm just trying to give you a little background. That's why it's in such a weird fashion. It's not just that number there is the period. You have to actually put it in that form in order for it to work. Then you can look here. You can see we'll have a horizontal shift right here. That's noted right there. And then we'll have vertical shifts right here. And that's noted right there, the vertical shift. So everything on here is noted in this picture, and you can see how we could actually come up with these. Now these rules also work for cosines, because you should note that cosine of x is simply a sine of x plus pi over 2. They are just shifted, horizontal shifted versions of each other, which means you can go right through and use all these same ideas, but on cosines. The amplitude out in front, the same period, all that kind of stuff. You have to be careful trying to use all these things, at least for the period. Be very careful about this. I'm going to show you in a minute about this, using that 2 pi over b as the period, the b is the period, for tangents and cotangents. It doesn't quite work there, and